All right, so let me go back to the PowerPoint. Okay, so that's basically what is called the photoelectric effect, all right, which is another additional experimental evidence of the fact that radiation exists not only as a waveform, but also as a stream of particles, and the name given to the particles are photons, all right? Okay, all right, so with that said, I'm going to get you started on assignment number 7. Sorry. And let me see who's out there in Zoom. I think I have published. Okay, only one person out there in Zoom. So for you, let me check to make sure that I've published assignment number 7. Yes, it's published. So let me download it. Yes, ma'am.
When's assignment 6 due?
Oh, I didn't set up a Dropbox for that?
Yeah.
I thought I did. Let me look at that now. Assignment number 6. Oh, okay. Let me see here. Okay, I'm going to let it be due tomorrow. No, what am I doing? Yeah, tomorrow. And let me go here. So it's available from today until tomorrow at midnight. All right? Okay, so let me set up this tablet here. And okay, so chapter 7, assignment 7. So we should be able to do the first couple of problems. 1, 2. Let me just check here. 3, 4. Okay, first 5 questions we should be able to do. So let's start off with number 1, which says an FM radio station broadcasts at 95.5 megahertz. Well, let me see, is this one working? Go back to share my screen. Let me see if this works. Okay, this works. Let me change the color. All right, so this question says, an FM radio station broadcasts at 95.5 megahertz and is asking for you to calculate the wavelength of the corresponding radio waves, right? So the equation, of course, that we're going to use is C is equal to lambda times nu. And remember, we said that the speed of any form of radiation, including, broadcast radio station signals, is equal to a constant, 3.00 times 10 to the 8 meters per second, all right? So in this case here, the question is asking for the wavelength, which is lambda, and by rearrangement of the original equation, that will be equal to C over nu. Now C is, as I said before, 3.00 times 10 to the 8 meters per second, and nu, which is the frequency, is 95.5 megahertz. But we have to do some conversion here. right? We have to convert the megahertz to seconds to the -1. Seconds to the -1 is the same thing as hertz. So therefore, we can say that 1 megahertz is equal to 1,000,000 hertz, or 1,000,000 seconds to the -1. And then we do that number crunching in the calculator. So that would be 3 times 10 to the 8. Okay, what's going on? 3 times 10 to the 8. Okay, my calculator is not behaving itself for some reason. Okay, divided by 95.5 times 10 to the 6. And according to my calculation, this works out to be equal to, when rounded off to 3 sig figs, 3.14, and the units here would be meters. The hertz, the megahertz will cancel, the seconds to the -1 will cancel, and that leaves the meters unit as a final unit. So that's a relatively simple problem. Any questions about this? Any questions? Any questions? All right. Let me clear this. And scroll down to the next question, which says, a laser in an audio compact displayer. This uses light with a wavelength of 7.80 times 10 to the 2 nanometers. Calculate the frequency of this light. So in this case, the equation that you'll be using is the same one, excepting that you're going to solve for the frequency, which is C over lambda, right? So C is, again, always 3.00 times 10 to the 8 meters per second, divided by the wavelength, which in this case is 7.80 times 10 to the 2 nanometers. So again, we have to do some conversion here. We have to convert a nanometer to meters. And what's the relationship? Nano means 10 to the -9. So therefore, 1 nanometer will go down here, 10 to the -9 meters upstairs. And then we do the number crunching. Divided by 7.80 times 10 to the 2. Okay, so according to my calculation, please check to make sure I'm doing the right thing, but I got 3.85 times 10 to the 14, and the final units here would be seconds to the -1. Nanometers will cancel out, meters will cancel out, and you get your answer expressed in units of seconds to the -1, which of course, again, is the same thing as hertz. All right? Okay, any questions about this one? Any questions? Any questions? Okay, so let me clear this and scroll down to the B part. And the B part is asking for the energy of a single photon of this light. So the formula that we are going to use is what we just talked about, and that is energy is equal to h nu. And based on the information provided earlier in the question, nu is, oh, they didn't provide it. We worked it out. I just erased it. What was the frequency we calculated? Can somebody remind me?
3.85 times 10 to the 4.
3.85
Yeah.
times 10 to the,
1.
and this would be seconds to the -1, right? Okay, so this is the formula we're using. Remember, H is Planck's constant, which is 6.63 times 10 to the -34 joules second. And then we multiply by the frequency, as she just mentioned, 3.85 times 10 to the 14. The second will cancel out with the second to the -1 here. So all we have to do is multiply those two. 6.63 times 10 to the minus 34. And then I'm going to multiply that by 3.85 times 10 to the 14. And according to my calculation, this works out to be equal to 2.55 times 10 to the minus 19 joules. And that's it. So that would be the energy carried by one photon. All right. Okay, any questions about this one? Any questions? Any questions? All right. Let me clear this and scroll down. Okay, so this one says, number 3, microwave radiation has a wavelength of the order of 1.0 centimeters. Calculate the frequency and the energy of a single photon of, oh, I just realized there's a typo here. Basically, I repeated the same question, so just scratch out this right here. Scratch out that part, because that's the question I'm asking in A. Okay, so the question is asking for the frequency and energy. So again, the same formula will be used. Frequency will be equal to C over lambda. So in this case, the frequency would be equal to C, which is 3.00 times 10 to the 8 meters per second, divided by the wavelength. Now, this time the wavelength is given as 1.0 centimeters. So we have to convert this to meters. So basically, 1 centimeter is the same thing as 10 to the minus 2 meters. So that's how we represent this here. And then we just put the numbers in our calculator to see what that gives. So 3 times 10 to the 8 divided by 1 times 10 to the minus 2. And according to my calculation, this works out to be equal to 3.0 times 10 to the 10. And the units here would be seconds to the minus 1. And that's it. All right. And then now the frequency, I'm sorry, not the frequency, the energy, the formula for calculating the energy is this, which we used before, right? So to calculate the energy in this case is going to be 6.63 times 10 to the minus 34 joules second times the frequency, which is 3.0 times 10 to the 10 seconds to the minus 1. And that's basically the setup. So multiply by 6.63 times 10 to the minus 34. Okay, so according to my calculation, rounded off to 2 sig figs, the answer will become 2.0 times 10 to the minus 23. And that would be the energy, and that would be in joules, by the way, joules, because this cancels with that, all right? Okay, any questions about the A part? Any questions? Any questions? Okay, now the B part is asking for the energy of an Avogadro numbers of these photons. Well, that's very simple, because we know that Avogadro's number is 6.02 times 10 to the 23. So all we have to do is multiply that by 2.0 times 10 to the minus 23. And that's it. So let's see what that gives. So according to my calculation, this rounded off to 2 sig figs would be 12. So this is in joules, so this would be 12 joules. And that's how that will be done. All right. Any questions? Okay, let me clear this. And let me see what is next. Oh, okay. So that's the end of question number 3. Okay, so in the case of question number 4, it gives you the wavelength of radiation produced by mercury, right? 2 wavelength values, which are given here and here, right? So the question is asking for you to calculate the frequencies of these emissions. What I'm going to do is basically calculate the frequency for one of them, right? And then I'm going to leave the other one for you to do, right? So I'm just going to focus on the first one, 404.7 nanometers. So to calculate the frequency, again, we're going to use the same formula. Nu is equal to, so this is 4, lambda equals 404.7 nanometers, all right? So to calculate the frequency, that will be equal to C over lambda, which is 3.00 times 10 to the 8 meters per second over 404.7 nanometers, which you have to convert to meters. So you have 1 nanometer here, 10 to the minus 9 meters above, and then we work that out. So let's see what that gives. 3 times 10 to the 8 divided by 404.7 times 10 to the minus 9. And according to my calculations, this works out to be equal to 7.41 times 10 to the 14. And the units here would be seconds to the minus 1 or hertz. All right? So that's a calculation for the wavelength of 404.7. And you're going to do a similar calculation for the other wavelength, 435.8 nanometers. All right? Okay, the next question is asking for the energy of a single photon for each wavelength. So again, I'm going to focus on the first one, and that would be energy is equal to h nu, which is equal to 6.63 times 10 to the minus 34 joules second, multiplied by the frequency that we calculated in the first part, 7.41 times 10 to the 14 seconds to the minus 1. So let me see here. So that times 6.63 times 10 to the minus 34, and then multiply by 7.41 times 10 to the 14. So I got, rounded off to 3 sig figs, 4.91 times 10 to the minus 19. And the units will be joules, all right? So again, you're going to do a similar calculation for the other wavelength. All right, any questions? Any questions? Okay, let me clear this and scroll down.
Do you maybe have 2 more of the shop itself worksheets, or do you have?
I'm sorry? Oh, you guys are pinning it? Oh, sorry, not bad. Okay, so the next question is calculate again, there's another typo here. This question should say calculate the energy of a mole of photon. So please make a note of that. Calculate right here the energy of a mole of photons. What is going on here? Why is this thing? Okay, I don't know what's going on with this thing here. It's not. Another. Same thing happening. Okay. Okay, so that's the correction. Energy of a mole of photons. Okay, so the question is asking, calculate the energy of a mole of photons of light with each of these wavelengths. So basically what you're going to do is take whatever the energy that was calculated in the B part, which I erased. Can somebody remind me what that energy is?
4.9.
Okay. 19 joules. So this is the energy per mole of photons, right? Or per photon, I should say, right? So for 1 mole of photons, we're going to multiply that by Avogadro's number. So 6.02 times 10 to the 23 photons per mole, right? So the photon units will cancel out. So your answer would be joules per mole. So let's see what that gives. So 6.02 times 10 to the 23 divided by, or not divided, multiplied by 4.91 times 10 to the minus 19. And when rounded off to 3 sig figs, I got 2.96 times 10 to the 5 joules per mole. All right. Any questions about that one? Any questions? All right. Let me clear this. So again, you're going to do the same calculation for the other wavelength. All right. Okay, let me clear this here. And let me scroll down. Okay, so now we have to go back to the PowerPoint because the next question has to do with something that we have not touched on yet, and that is the Bohr model. So this guy, Niels Bohr, very important figure in the history of science, especially as regards to trying to understand the nature of the atom. So he found through some experiments that he did was that the electron energy in an atom is quantized. And what that means is that the energy of the electron can only have certain specified discrete values, all right? So he probed into it and he came up with an idea, a model that explains this observation, right? As stated here, each specified energy value that the electron can have is called an energy level, right? So he came up with a model of the atom, and this model was specific to a structure which has only one electron, like, for example, the hydrogen atom. Basically, what he's saying is that the electrons in the atom, or I should say the electron, since we're dealing with a one electron atom, basically the way they exist in an atom is that they exist within what are called orbits, right? In fact, in some textbooks, they call this the planetary model, kind of similar to the sun. Of course, you have different planets going around the sun. So he was proposing the same thing, right? That basically you have the nucleus in the middle, and then you have orbits that are around the nucleus, and the electrons can only exist within those orbits. And those orbits have associated with them specific energy values, right? So this is his model right here. The first orbit, he calls it the n equal 1. Then the next orbit is the n equal 2, and so on, right? And you can go all the way up to n equal infinity, all right? So therefore, according to Bohr, the electrons, while they are in a particular orbit, will have a certain amount of energy, right? Now, they can be promoted from one orbit to another, or they can fall from one orbit to another if, well, let's talk about the electrons moving from a lower orbit to a higher orbit. According to Bohr, an electron can do that if it gains enough energy to make that move. So for example, if the electron gains enough energy to go from the n equal 1 to n equal 2 orbit, then it will do so, right? Or n equal 1 to n equal 3, and so on, right? And we call those types of movements electron excitation, where the electrons are moving from a lower energy orbit to a higher energy orbit. You can also have the reverse, where the electron is falling from a higher energy orbit to a lower energy orbit. And that is called electron, well, that will cause light emission. And that's because as you go from a higher orbit to a lower orbit, it loses energy. And that energy will be released in the form of radiation, all right? So that's basically what the Bohr model says. And he came up with an equation, which is this right here. En is equal to minus RH over n squared, which represents the energy of a particular orbit, right? So n is the n value that we were just talking about here, and RH is a constant known as the Rydberg constant. That is equal to this value right here, 2.18 times 10 to the minus 18, right? So if you want to calculate the energy of each of these orbits, then all you have to do is put in the n value, and that will give you the energy. And based on that, you can calculate the difference in the energy levels where you have an electron either undergoing excitation or undergoing, the other term is relaxation, when it falls from a higher orbit to a lower orbit. In fact, oh, I thought I had the equation right here. So stated here, the negative sign represents forces of attraction. That's this negative sign here, very important. And the energy is 0 when n is infinity, right? So if the electron is far away, like extremely far away from the nucleus, then as far as its energy in relation to the atom or to the nucleus, it will be 0, all right? Okay, so this is the equation that you're going to use to calculate the difference in the energy level that, that one can observe when you have an electron moving from one energy level to another, right? So this here represents the formula for the final energy level, energy. This represents the energy of the initial energy level. And therefore, you can find the difference in the energy levels by subtracting the final, well, the initial from the final. So this is the setup right here, right? Which turns out to be equal to this. Minus RH 1 over ns squared over 1 over ni squared. I like to use 2 on 1. In other words, the way I like to represent it is that delta E is equal to minus RH 1 times 1 over n2 squared minus 1 over n1 squared, where n2 and n2 would be the final energy level, n1 would be the initial, right? So this is saying the same thing as this. This is just my preferred way of expressing it, all right? So that is a formula that you can use to calculate the change in energy, right? And it's very important that you, again, set this up so that you have the final n value here and the initial n value here, right? That's very important. Also very important, the negative sign, all right? Okay, so this is just basically a diagram showing you, in the case of hydrogen, the different types of transitions as you have the electrons falling from higher orbits to lower orbits and the type of radiation that's emitted. And they're clustered in what are called series, right? So basically, this series right here, where you're having electron transitions from higher orbits to n equal 1, that's called the Lyman series, right? And then we have the Balmer series, where we have electrons falling from higher orbits to n equal 2. And then we have the Paschen series, where you have electrons falling from higher orbits to n equal 3, all right? Now, the thing is that the only radiation that can be visible as a result of these emissions would be the ones in the Balmer series, right? These falls within the visible part of the electromagnetic spectrum. The others, basically, in order for you to observe them, you'd have to use some instruments, special instruments to show that these actually are produced, all right? When you have the electrons falling from higher orbits to lower orbits in the Lyman and Paschen series. Okay, some other things we need to talk about here. Hold on 1 minute, let me just check something here. Okay, something I need to mention before getting into that discussion. Let me get out of this here and go to Word. Because you might find different things stated in different textbooks. So I'm just going to give you some information here. Okay. Now remember the equation I just showed you. And that is delta E is equal to minus RH times 1 over n2 squared minus 1 over n1 squared, right? Now, back when I was a student, when I first learned this, I knew this to be the Rydberg equation, all right? And the Rydberg constant is RH, which is equal to 2.18 times 10 to the minus 18 joules, right? So that's what I learned way back when, all right? Now, we know that delta E is equal to h nu, right? The energy that is emitted or absorbed will be equal to the Planck's constant times the frequency. And we also know that nu is equal to c over lambda. So what we can do is plug this where nu is, and you're going to end up with hc over lambda, right? And that would be equal to minus RH times 1 over N2 squared minus 1 over N1 squared, right? So we can divide both sides by HC. So let me just do this here. HC, divide both sides by HC. So this will cancel out with that, and you're going to end up with this equation. 1 over lambda is equal to minus RH divided by HC times 1 over N2 squared minus 1 over N1 squared. Now this minus RH, or I should just say RH over HC, is a collection of constants. So RH is a constant, H is a constant, C is a constant. So let's see what that gives. RH is 2.18 times 10 to the minus 18 divided by H, which is 6.63 times 10 to the minus 34 times C, which is 3.00 times 10 to the 8. And according to what I got here, all of this turns out to be equal to minus 1.10 times 10 to the 7. And the units for this would be meters to the minus 1. All right? So that would be multiplied by 1 over N2 squared minus 1 over N1 squared, right? Okay, now here's the thing that might sound a bit weird. Nowadays, in some textbooks, I don't remember if this is true in your textbook, this is called the Rydberg equation. In fact, some textbooks say that this is the Rydberg equation. Other textbooks say that this is the Rydberg equation, all right? And they call this here RH. Back when I learned it, they called that RH, right? So I'm just showing you this to show that, you know, if you look in your chemistry textbook or if you look in other sources, even online, I've checked online and I've seen both alternatives shown and expressed, right? So I'm just showing you this so that you're not confused. What I will say is that both forms are useful, right? This form is useful if you want to find the difference in the energy of the transition as the electron goes from one orbit to another. This one is useful if you want to find the wavelength of the transition, right? So the one that you're going to choose is dependent on, you know, what the question is asking for, right? One thing I need to say, and I don't think I have it in the PowerPoint, when it comes to delta E, all right? If the transition is from a lower to a higher orbit, when you do the calculation, put in all the values, you're going to see that delta E is positive, which makes sense. You know, the energy increases, right? If you have an opposite transition, the electron falling from a higher orbit to a lower orbit, then delta E would be negative, right? Makes sense again, right? If you do the same thing with the wavelength equation right here, what you're going to find is that, again, if the transition is positive, the wavelength that you're going to calculate directly from this would be positive, right? And then if the transition is the other way around, the wavelength is going to be negative. But the key thing is that you need to recognize is that there's no such thing as a negative wavelength, right? What you need to do is interpret the sign, meaning that, okay, the wavelength is this value, and that's the wavelength of the radiation that will be emitted as a result of the electron falling from a higher orbit to a lower orbit, right? So that's just one key thing that you need to remember when using this equation here. If the wavelength is negative, it doesn't mean that there's a negative wavelength. What it means is that the wavelength value that is given is the wavelength of the radiation that's emitted. All right, so that's the way you interpret that sign. All right, so I just thought it was important to show you the two alternative ways of determining, of expressing the Rydberg equation. All right, so any questions about this? Any questions? Any questions? All right, so going back to the PowerPoint. Okay, so let's talk about ground states and excited states. Electrons in their lowest possible energy levels are said to be in the ground state, right? Now, if you have the electron promoted from the ground state, then that state was called the excited state, all right? So that's the definition of the ground state. The ground state is the lowest possible energy state, and any other state would be excited state. So you can have the electrons promoted from lower energy levels to higher energy levels by several means, as you can see here. Electric discharge, which is what is used in those lamps I showed you earlier, with the hydrogen lamp, for example. You can use electrical discharge, you can use heat, and you can use lasers, all right? And then what happens is that excited state is unstable, and therefore any chance the electrons get will fall back to the lower ground state, and therefore radiation will be emitted, and that's called relaxation. Okay, so this is just some examples of where you have electronic transitions. If you look at, for example, the electron transitioning from n equal 1 to n equal 5, represented by A, basically that's an excitation. It's going from a ground state to a higher state, right? And that corresponds to an absorption of energy, right? And then in terms of the ones where you have electrons falling, excuse me, from a higher energy level to a lower energy level, like in the case of going from n equal 4 to n equal 2, or n equal 4 to n equal 3, or n equal 3 to n equal 2. In those cases, energy would be released in the form of radiation, and we call those processes relaxation. Okay. Some other things we need to say about this is that the energy gap that is represented by the length of the arrows here is inversely proportional to the wavelength. And if you think about it, it makes sense, because going back to this equation here, where shall I put it? Let me put it up here. Remember, delta E is equal to h nu, which is the same thing as hc over lambda, right? So delta E is the energy gap of the transition. The wavelength is down here. So there's an inverse relationship between the energy gap and the wavelength. So the bigger the energy gap, the smaller the wavelength of the transition, and vice versa, right? So that's basically what they're saying here. Shorter wavelength corresponds to higher energy gaps, right? Longer wavelength corresponds to lower energy gaps, all right? So that's another relationship that is a result of these energy transitions. Okay, so now, based on what we have just covered, going back to the assignments, we should now be able to do question number 5. Let me see. Let me scroll down and see what. So we should be able to do 5. We should be able to do 6. We should be able to do 7. We should be able to do 8. Okay, so those are the questions we're going to focus on right now. Okay, so let's look at number 5. Calculate the longest and shortest wavelength of light emitted by electrons in the hydrogen that begins in the n equals 6 state and fall to states with smaller values of n. Now, I like to see things kind of pictorially. So when I'm given a question like this, I would do something like this. Hold on. Let me, no, that's too small. I would like to draw a little diagram, something like, okay, so, what if I can fit it here? Okay, let me try down here. So this would represent n equal 1, this line here, and then n equal 2, which is this line here. And then as you go up, what you'll find, and I probably should have mentioned this before, the energy gap becomes smaller as you go up, right? So this gap here would be the largest gap, and then n equal 3, n equal 2 gap would be smaller, and then n equal 4 would be even smaller, and then when you get to n equal 5, the gap decreases again. All right, and then n equals 6. All right? Okay, so what the question is asking is what would be the longest and shortest wavelength as the electron, so let's say the electron is here, right? It falls to lower energy levels, right? So basically, the smallest energy gap would be from 6 to 5. And that would correspond to the longest wavelength, as I said before, right? So I would say for the longest wavelength, the energy gap would be from n equals 6 to n equals 5, which is the shortest energy gap. So delta E, lambda, okay. So to calculate lambda, this is the equation I would use. 1 over lambda is equal to minus RH times 1 over final, which is 6 squared, minus 1 over initial, which is 5 squared. Now, in this case, RH is equal to, if I remember correctly, 1.10 times 10 to the 7 meters to the minus 1. Can somebody confirm that? I gave you guys that earlier, right? Okay, good. So that would go here. So I'm just going to put that here. Minus 1.10 times 10 to the minus 10 to the 7. Not, it's 10 to the 7, right? Right. M to the minus 1. Times 1 over 6 squared minus 1 over 25 squared. And that's basically what you need to work out. So what I would do is, I'm sorry, I said 25 squared, it should be just 5 squared. So what I'm going to do is, I'm going to do the calculation first within the parentheses, which would be 1 divided by 36 minus 1 divided by 25. And so this part here, I got minus, oh shoot, okay, my bad. These should be reversed because n equal 5 is the final energy level of the transition and n equals 6 is the initial because you're starting from 6 and going down, all right? So I'm sorry about that. All right, so that means I need to change this as well. So this would be 5 squared and this would be 6 squared. Okay, so let's do that calculation. So 25. Oh. Okay, so for this part here, I got 0.0122, all right? And then I'm going to multiply that by 1.1 times 10 to the 7, right? And when I did that, I got rounded off to 3 sig figs. I got 1.34 times 10 to the 5. Now, please note that this unit here is meters to the minus 1, and that is 1 over lambda. But the question is asking for lambda. So lambda is equal to 1 over 1.34 times 10 to the 5 meters to the minus 1. So let's see what that gives. So according to my calculation, this gives 7.44 times 10 to the minus 6 meters. And that should be the answer. All right? So that's basically how you do that. And that's for the longest wavelength, right? So how do you think we would get the shortest wavelength? The calculation that we just did is for the longest wavelength. So how do you think we would get the, or how do you do the calculation for the shortest wavelength?
Between n equals 2 and n equals 1.
Nope. You're starting from n equals 6. And it's falling to lower energy levels. We just did the transition from n equals 6 to n equals 5. That gap is the shortest energy gap, which gives the longest wavelength. I'm sorry?
6 to 1.
6 to 1, exactly. So basically, you're going to change the n equal 5 here to 1, which means that here, you're going to have 1 squared, which is 1. And you're going to have that down here as well. 1. So let me do that calculation. 1 minus that. Okay, so when I did that, I got times 0.972, and then I'm going to multiply that by, hold on. Okay, let me just erase this here to avoid confusion. I'm going to multiply that by minus 1.10 times 10 to the 7. I just realized I should have made a point for the first part. You're going to end up with a negative sign here. Going back to the first part, the shortest wavelength, you're going to end up with a negative sign here, right? So that would be negative. But of course, your final answer would be positive because as we said before, there's no such thing as a negative wavelength, right? So just to keep that in mind, right? And the same thing is going to happen in this case. So let me erase this right here and do this calculation. Okay, so 0.972 multiplied by 1.1 times 10 to the 7 negative. No, not negative there, but okay. So round it off to 3 sig figs. You're going to get, again, a negative value. Minus, in this case, 1.07 times 10 to the 7 meters to the minus 1. And this is 1 over lambda, by the way. So let me change this right here. So this will be 1 over lambda, which means that lambda would be equal to 1 over minus 1.07 times 10 to the 7 meters to the minus 1, which would be equal to 9.35 times 10 to the minus 8, minus 9.35 times 10 to the minus 8 meters. But again, the final answer is going to be 9.35 times 10 to the minus 8, right? Again, because the negative sign indicates that radiation is emitted, all right? And that's how you're going to do number 5, all right? Okay, any questions about this one? Any questions? Any questions? No questions? Okay, let's clear this and move on to the next question, which says, calculate the change in energy when an electron transitions from n equal 3 to n equal 2 in a hydrogen atom, and what does the sign of the energy signify? So basically, in this case, you're calculating the change in energy. So the form of the equation that you're going to use is delta E is equal to minus RH times 1 over NF squared minus 1 over NI squared, all right? So in this case, the RH value you're going to use is 2.18 times 10 to the 18 joules. I'm sorry, 10 to the minus 18 joules. And then you're going to multiply that by 1 over N final. Now what's N final? 2 squared, right? Minus 1 over N initial squared, which is 1 over 3 squared. And that's it. That's the setup. So let's see what that gives. I'm going to work out again what's within the parentheses here. So that's okay, so according to my calculation, this part here works out to be 0.139 multiplied by minus 2.18 times 10 to the minus 18 joules. And let's see what that gives. So that times 2.18 times 10 to the minus 18. And according to my calculation, this works out to be 3.03 times 10 to the minus 19 joules. And that's how you do that. Oh, minus, don't forget the minus, right? And the question is asking, what does the sign of the energy signify? And that signified what? Because the sign is negative for the change in energy, that signifies what? Right, the electron transition is going down, which means that radiation would be emitted, right? Or energy will be emitted, all right? So we can write down here that energy is emitted. And that's it, all right? Okay, any questions about this one? Any questions? Any questions? Okay, so let me clear this. Let's put it down. Okay, now this question says, using the Rydberg formula, calculate the initial energy when an electron in a hydrogen atom transitions from n equal 2 and emits a photon at 410.1 nanometers, all right? And I want to stress one important point being made in this question, and that is it emits a photon. What does that tell you? Exactly. The change in energy will be negative. All right, very good. So basically, let me see here. So because they gave the wavelength here, I would use this formula. 1 over lambda is equal to minus RH times 1 over N2 squared minus 1 over N1 squared, right? So let's see here. They gave you, okay, so they gave you the final energy level, which is N equal 2, and they're asking for basically the initial, which is N1, all right? So what I would do is, firstly, I would just put the numbers in. So 1 over lambda. Now, lambda is equal to 410.1 nanometers. I would convert that to meters. You're going to have 1 nanometer here, 10 to the minus 9 meters. And because radiation is emitted, I'm going to put a negative sign there, right? Again, remember, there's no such thing as a negative wavelength, but because the radiation is emitted, you have to put a negative sign there, right? And then that would be equal to minus RH. Now, RH in this case would be 1.10 times 10 to the 7 meters to the minus 1, and then multiplied by 1 over the final N value, which is 2 squared, minus the initial value, N value, which is N1 squared, right? So this is what we're trying to find. So we're going to do some math right here, some rearrangement and so on. What I would do first is divide both sides by minus 1.10 times 10 to the 7 meters to the minus 1. So I'm going to do that here and do that here. Minus 1.10 times 10 to the 7 meters to the minus 1, right? So some units will cancel out, nanometers will cancel out here and here. Meters will cancel out with the meters to the minus 1. So I'm just going to work out what, and these two will cancel out. This will cancel out with this. So I'm just going to work out the right side first. So that's 410.1 times 10 to the minus 9 times 1.1 times 10 to the 7. And then I'm going to put that under 1. So for this part here, I got 2.22 times 10 to the minus 1, which is the same thing as 0.222. Oh, by the way, this negative sign will cancel out this negative sign, right? So therefore, that side will be positive. Now that would be equal to 1 over 2 squared minus 1 over N1 squared, right? Now 1 over 2 squared is the same thing as 0.25. So let me just do that, right? So now what I'm going to do now is solve for 1 over N1 squared. And that would be equal to 0.25 minus 0.222. So that would be equal to okay, so according to my calculation, that would be equal to 0.028. So therefore, n1 squared would be 1 over 0.028. Let's see what that gives. That gives 35, which means that n1 squared is n1, I'm sorry, is equal to the square root of 35. Which is equal to 5.9. Now, because we know that the n value must be an integer, hold on, is that right? Oh, right, okay. Because n1, or the n values, n1, n2, whatever, because n1 must be an integer, basically what we can do from here is round this up to 6. So that would be the final answer. And that's how you do that. All right? Okay, any questions about this one? So this one is kind of important in terms of reading the question carefully. All right? Because the question says the atom emits a photon. You have to remember to include a negative sign to indicate that radiation is emitted. All right? Okay, any questions about this one? Any questions? Any questions? No questions? All right, so I take it I can clear this, right? All right, so let me scroll down. Okay, let's see number 8. Use the Rydberg equation to calculate the wavelength. Okay, let me hear what you guys have to say about this one. You guys should be able to do this with minimal help from yours truly, based on the first 3 questions that we looked at. So it says you're to calculate the wavelength. Now remember, I gave you 2 forms of the Rydberg equation, right? Which form would you use in this particular case? Which form of the Rydberg equation would you use in this particular case? 1 over lambda is equal to 1.10 times 10 to the 7 meters to the minus 1 times 1 over n2 squared minus 1 over n1 squared, right? Okay, so what next? A negative, yeah, thank you very much. Very important, thank you. Negative should be there, always. Unless you switch these two. If you switch these two, then it's going to be positive, but I prefer to have it this way, all right? All right, so what next? Okay, so minus 1.10 times 10 to the 7 meters to the minus 1 times 1 over n2 squared, which is the final, which is 3 squared, right? Minus 1 over n1 squared, which is 1 squared. So let's see, I'm going to work out again this part right here. So that's okay, so according to my calculation, this part here is minus 0.889. And I'm going to multiply that by minus 1.10 times 10 to the 7 meters to the minus 1. So according to my calculations, this works out to be equal to 9.78 times 10 to the 6 meters to the minus 1. What next? What I got so far is 1 over lambda. So what next?
Yeah.
Right, so lambda would be equal to 1 divided by 9.78 times 10 to the 6. And let's see what that gives. And this is meters to minus 1 down here. So let me do that. And I got, and again, please correct me if I'm wrong, but I got 1.02 times 10 to the 7, 10 to the minus 7 meters. All right, and that's how that is done. All right. Any questions about this? Any questions? Any questions? All right. Let me clear this and scroll down. Okay, so let me go back to the PowerPoint now to talk about this equation here, known as, and I don't know if there's anybody who speaks French here, but I'm about to massacre this guy's name, so my apologies. De Broglie, somebody pronounced it to me some time ago, and I don't remember. De Broglie's equation, right? So de Broglie, he was looking at all the information that was gleaned so far, all the information that we talked about with respect to radiation behaving like a waveform and also behaving like a stream of particles. So what de Broglie was considering was, okay, if that is true for radiation, is it possible that any ordinary object that is moving will have an associated wavelength with it, all right? So he did some theoretical work and he came up with his equation, his famous equation, which is known as the de Broglie equation, which is given right here. Basically what he's saying here is that any object that is moving, and it says here particle, but this literally can be applied to any object that is moving at a certain speed, then there's an associated wavelength which can be calculated based on the equation that he derived. And that equation is right here. Lambda is equal to h over mv, where lambda is the wavelength associated with the moving particle, h is Planck's constant, m is the mass of the particle, and v is the velocity. And in terms of the units, actually, let me just write them here. The units for h is joules second, the units of m is kilograms, and the units of velocity would be meters per second. So if these are all the units on this side of the equation, then the units of lambda would be meters, all right? So that's the de Broglie equation. And this equation has been successfully used to calculate wavelengths of particles especially. And this is one of those examples where somebody does something in the realm of theoretical science with no aim excepting to discover the results of the theoretical work. And in this particular case, it led to the development of the most powerful microscope known, which is the electron microscope, right? The electron microscope is more powerful because instead of using light, which ordinary optical microscopes would use, they use a stream of electrons. And what you'll find is that it's more powerful, the resolution is better, and so on, right? So this is one of those examples where somebody's theoretical work led to a very interesting and useful piece of technology. All right, so that's de Broglie's equation. And then we have the uncertainty principle, which was put forward by Werner Heisenberg, and in 1927, when my father was born. Anyway, basically what his principle says, and it's actually a mathematical equation, which I won't show you, but basically it says that we can't simultaneously know exactly where a tiny particle like an electron is and exactly how it is moving, right? And he did some theoretical work to show that, which basically signals the end of the Bohr model, because the Bohr model is assuming that there's some certainty in identifying where the electrons would be in orbits. That's what he suggested. What Mr. Heisenberg is saying is that that's not true, all right? So that basically represents using the Bohr model as an artifact more so than describing the reality of how the electrons are in an atom, right? Now, the reason why Heisenberg's principle is true is because of this last statement right here. The act of measuring the particle actually interferes with the particle. So just to illustrate that, I'm going to show you this diagram here. Let me clear this writing first. So let's say, and this is of course purely theoretical, but it makes sense if you think about it. Let's say you have a special microscope which allows you to see an electron, right? So in order for you to see the electron, if it's an ordinary optical microscope, then a photon of radiation would have to hit the electron and then move towards the microscope so that you can see the electron at that instant. The problem is when the photon hit the electron will move. So what you'll be seeing is not where the electron was at that instant. It's after, what you will see is after where the electron was after impact with the photon. So that's basically a simplified way of explaining the uncertainty principle, right? So let me see here. And as a result, as I said before, the Bohr model fails, right? Because as I said before, the Bohr model assumes that there's some certainty associated with the location of the electrons within orbits. So therefore, a new model would have to be created or derived in order to explain further the arrangement of electrons in atoms. Now, based on what we have covered so far, going back to the assignment, we should now be able to do, let me see here, questions 9A. Okay, 9A and B, all right? So both questions, the A part and the B part, is based on the Broglie equation, all right? Which is lambda is equal to H over mv. Now remember, H is Planck's constant, m is the mass in kilograms, and v is the velocity in meters per second, and lambda would be the wavelength. So in this particular case, the question is asking, what is the velocity of a neutron? And it gives you the mass of the neutron, which exhibits a wavelength of 580 nanometers. So what the question is asking for is v. So we'd have to rearrange this equation to get v is equal to h over m times lambda, right? So h, as I said before, is 6.63 times 10 to the minus 34 joules second divided by the mass. Now the mass is given as 1.67 times 10 to the minus 24 grams, but we have to convert that to kilograms. So we're going to put 1,000 grams here, 1 kilogram here, and then we multiply by the wavelength. Now the wavelength, is given in nanometers. We have to convert that to meters. So 580 nanometers, we have to convert to meters. Nano means 10 to the minus 9. So that means that we're going to put 1 nanometer here and 10 to the minus 9 meters above, right? So that's the setup. And all we have to do is crunch the numbers. So what I'm going to do is I'm going to do the denominator first. 1.67 times 10 to the minus 24 times 580 times 10 to the minus 9. And then I'm going to put 1 over that. And then I'm going to multiply that by 6.63 times 10 to the minus 34. And according to my now this, I have to round off to 2 sig figs. So according to my calculations, this works out to be equal to 6.8. Oh, wait a minute. Did I divide by 1,000? Let me try this again. I think I skipped. Let me try this again. 1.67 times 10 to the minus 24. And then divide by 1,000 times 580 times 10 to the minus 9. And then I put that under 1, and then I multiply by 6.63 times 10 to the minus 34. Okay, so I skipped the part where I should divide by 1,000. So according to my calculations, the answer I got is rounded off to 2 sig figs, which would be 0.68, and the units would be meters per second. And that's how that is done. All right. Any questions about this one? Any questions? Any questions? Any questions? No questions? All righty. Let me clear this and scroll down. Okay, now this one. Okay, this one is basically asking the same thing. It's asking for, oh, actually, no, it's not asking for the same thing. It's asking for the wavelength. It's the same equation that you're going to use, which is lambda is equal to h over mv, right? But you're going to, the question is asking for the wavelength. So you're just going to put all the numbers in that equation. So h, again, is 6.63 times 10 to the minus 34 joules second, divided by the mass, which is 9.11 times 10 to the minus 28 grams, which we have to convert to kilograms. So again, 1,000 grams down here, 1 kilogram above, and then we multiply that by the speed, which is 500.0 meters per second. And that's it. So let's do the number crunching again. I'm going to work out what's below. 9.11 times 10 to the minus 28 times, or divided by 1,000, times 500. And then I'm going to put 1 over that, and then I'm going to multiply that by 6.63 times 10 to the minus 34. Oh, shoot, I made a mistake. Let me do this again. 9.11 times 10 to the minus 28 divided by 1,000 times 500, and then 1 over that. And then I'm going to multiply by 6.63 times 10 to the minus 34. Okay, so the answer I got, and again, please correct me if I'm wrong, I got, now in this case, I have to round off to 3 sig figs. So I got 1.46 times 10 to the minus 6. And the units here would be meters. And that's how I did that. All right? Any questions about this one? Any questions? Okay. Let me see. Let me clear this. And scroll down. Oh, okay. So we can't do number 10 right now. So we have to go back to the PowerPoint. Okay. So this is where things get really complex. And thankfully for you guys, you don't have to do much in terms of delving into the details of this. And let me warn you, this is a bit abstract, all right? I remember watching a video. I don't know if you guys have ever heard of this famous biologist by the name of Richard Dawkins. He's famous for talking about science and all that. And he said that he had a conversation with a physics person who's a quantum mechanics expert. And he says that this expert says that if you think you understand quantum mechanics, you don't understand quantum mechanics, right? It's very complex. There's a lot yet to be discovered, and there are people who are working on quantum mechanics right now, you know, trying to gain a more understanding about this material. So let me just warn you, this particular topic is very abstract. Unfortunately for me, when I was in grad school, when we did advanced physical chemistry, we had to do some calculations, which thankfully you guys don't have to do. And I graduated in 99 and I'm still recovering from that. So just to warn you, all right? So let me just give you a broad overview. Quantum mechanics. This has become necessary because of what I said before in terms of the uncertainty principle, right? So we know that the Bohr model is not really a true model as far as how the electrons are arranged in the atom is concerned. So basically, this guy by the name of Erwin Schrödinger, he came up with an equation to describe the behavior of the electron in the hydrogen atom. I will not show you that equation, right? I like you guys too much. So based on the equation that he derived, there's a solution to that equation, which is called a wave function, right? And the wave function basically represents the energy states of the atom that was previously put forward by Bohr, right? So basically, you still have energy levels, n equal 1, n equal 2, and so on. But the thing is that the electrons are not in orbits, as predicted by or as stated by Bohr in his theory, right? So the question now becomes, how do we interpret that wave function? Basically, the wave function, the way it is used to interpret, or what it is used to interpret, is the probability of finding an electron within a certain region of the atom. So therefore, there are no such thing as orbits, right, where the electrons are in clearly defined paths, right? Basically, as a result of the complex calculation that he did, he came to the conclusion that instead, for a particular electron, those electrons would be in a certain region, and there's a probability of above 90% of finding that electron within that region. So that region we call an orbit, or I should say orbital, right? Not orbits, all right? So basically this interpretation leads to the idea of as I said before, an orbital, which is basically considered to be like an electron cloud. The way I like to interpret it is that, let's say, and again, this is, this is kind of hypothetical. Let's say, for example, you have a special camera that can photograph an electron repeatedly, right, as it's moving, right? So basically, you take a picture and the electron is, let's say, hold on, what's going on here? Okay, the electron is, let's say, here, and then soon after, it's here, it's here, it's here, it's here, and so on, right? So you're going to have a lot of dots representing where the electrons are located, right? And what you'll find is that the electrons would have a probability which is relatively high within a certain region, let's say within this circle right here. You might find the electron from, occasionally, one might be there, and so on, right? So the region here where the probability of finding the electron is high, that's what we call the orbital, right? So that's the way I look at it, all right? If you could possibly take pictures repeatedly and locate where the electrons are in each photo and overlap them, you find that in most cases, the electrons would be within a certain region for the most part, and therefore that would be the orbital. I keep confusing the terms. The orbital, right? Not orbit. Okay, so again, as it relates to this equation here, there are certain numbers which are called quantum numbers, which relate to the energy levels and the orbitals within the energy levels, right? So basically, for the wave function to be solved, there are three what we call quantum numbers, right? In fact, there's a fourth quantum number, but I'm going to talk about that later on, right? So I'm going to get into all these different quantum numbers. A wave function with a given set of these three quantum numbers is called an atomic orbital, all right? And these orbitals allow us to visualize the region where the probability of finding an electron is high. I should have added that here. This should be is high, all right? So let's talk about the different quantum numbers. The first of which is what is called the principal quantum number, signified by the letter n. The same n value, by the way, which the Bohr model uses, n equal 1, n equal 2, all the way up, right, to infinity, right? So this quantum number is independent of all the other quantum numbers, right? And basically, it's a positive integer, as we said before, n equal 1, n equal 2, and so on, all right? And it turns out that the size of an orbital and its energy is dependent on n. So this is one thing that the Bohr model has in common with the quantum mechanic approach, in that the higher the n value, the higher the energy of the, well, in the case of the Bohr model, that would be the orbit, but in the case of the quantum mechanical approach, it would be the orbital, right? And then it says here that the size of the orbital also increases with the n value, all right? Orbitals with the same value of n are said to be in the same principal shell or energy level. So if you hear me use the term shell interchangeably with energy level, they both mean the same thing, all right? Okay, so that's the principal quantum number, the first one. The second quantum number is called the orbital angular momentum quantum number, symbolized by the letter L, right? And this determines the shape of the orbitals. Now remember, the orbitals are the region in space, in an atom, where there's a high probability of finding an electron, right? So basically, the values for the angular momentum quantum number, the L values, starts with 0 and goes up incrementally by an integer, right? Now, the values of L for a particular shell is dependent on the n value, right? As stated here. The possible values of L starts from 0 and goes to n minus 1, all right? So for example, if you're in the n equal 2 shell, right? Then there are only two possible values of L. 0, which is what we start off here, and then 2 minus 1, which would be 1, all right? So let's say, for example, just to give you another example, let's say that n is equal to 3. If n is equal to 3, then the possible values of L will be 0, 1, and then 3 minus 1, which is 2, right? If n is equal to 4, then what do you think the possible values of L would be, based on the trend that we're observing here? 0, 1, 2, 3, exactly. All right? Okay, now let me just say also, and I skipped over it here, the L value corresponds to the shape of the orbital. And there are some special letter designations for the particular orbitals of a particular shape. So if L is equal to 0, we call that an S orbital. Or right, if the orbital if the orbital has an L equals 0 value, it's called an S orbital. If L is equal to 1, we call that a P orbital. If L is equal to 2, we call that a D orbital. And if the orbital has an L value of 3, then we call that an F orbital. And then after that, it goes alphabetically, G, H, I, and so on. All right. So that's basically the L values. Let me see what I have here also. So each of these orbitals is a different region of space and also have different shapes. And we're going to get into the actual shapes of these orbitals shortly. Some of this, I think you should have met in your introductory chemistry or high school chemistry class. So let me erase all this here. Okay. Okay, what's going on here? Oh. Okay. Also, very important, all orbitals having the same value of n and the same value of L are said to belong in the same subshell, right? So if you have orbitals in, let's say, the second shell, then the subshells will be associated with, for example, L equal 1, right? All orbitals in L equal 1, or have a value of L equal 1, are said to be in the same subshell, all right? Okay, so that's the angular momentum quantum number. Then you have the third quantum number known as the magnetic quantum number, symbolized by ML. And basically, this ML value determines the orientation in 3 dimensions in space of the particular orbital that has a particular ML value. Now, the ML values is dependent on the L values, right? In that, the possible values of ML for a particular L value will go from minus L and all integers to plus L, right? So from minus L to plus L. So for example, if L is equal to 2, then the possible values of ML would be minus 2, minus 1, 0, 1, 2, right? And each of these ML values represents a particular orbital belonging to the L equal 2 sublevel, right? So remember now, in the case of L equal 2, this corresponds to a d orbital, right? And because we have ML is equal to possibly these 3, or these 5, I should say, that means that d orbitals, when they appear in an atom, they appear in sets of 5, right? So you always have 5 d orbitals. Let me give another example. Let's say L is equal to 0. What are the possible values of ML? Based on the fact that ML can go from plus L to minus L. 0, exactly. So therefore, L equals 0 corresponds to an s orbital. So therefore, you can only have one s orbital in any of the shells or subshells in an atom, right? Suppose L is equal to 1, which corresponds to a p orbital. What are the possible values of ML? If L is equal to 1, based on this right here. If L is equal to 1, ML values will be what? Plus 1, 0, and then minus 1. All right? So therefore, for p orbitals, they always appear in sets of 3s because each p orbital, there are only 3 p orbitals, each of them will have an L value, L1, L equal 1, 0, or minus 1. Okay, let me see here. And so on and so forth, right? So those are the ML values. All right, so this is a summary of the ML values, the N values, the L values, and what they actually mean. So as I said before, in the first shell where N is equal to 1, there's only one possible value of L, which is 0, one possible value of ML as a result, which is also 0. And therefore, the designation that we would use for the first shell in terms of the subshell, that would be 1s, right? And in terms of the number of orbitals present in that subshell, there's only one. And that is true for all the S subshells, right? And then now, here, where n is equal to 2, there are two possible values of L, 0 and 1, right? In the case of L equals 0, ML is equal to 0. The designation here will be 2s because it's an s orbital, L equals 0, and or s subshell, and n is equal to 2. And therefore, there's only one of them again because it's an s subshell, right? Where ML is only equal to 0. When we get to L equals 1, there are three possibilities, right? In terms of the ML values, -1, 0, +1. Those represent separate p orbitals within that same subshell. That's what's indicated here. So therefore, the total number of orbitals will be 3. And then when we get to the third shell, things become a bit more complicated because you can have n equals 3 in each case, but L can be equal to 0, 1, or 2, right? And then we have these columns for n equals 0, ML is equal to 0. That's a 3s designation, only one s orbital present when they appear. When L is equal to 3, you have three possible values of ML, -1, 0, +1. That represents three separate 3p orbitals. So therefore, that's why we have 3 orbitals here. And then now we get to where L is equal to 2. There are 5 possibilities, right? -1, -2, 0, +1, +2. Each of these represents a separate d orbital. So therefore, you have 5 3d orbitals, right? So basically, to summarize, s orbitals, when they appear singly. P orbitals, when they appear in sets of 3s. D orbitals, when they appear in sets of 5. And then for the F orbital, which is not shown here, for F orbitals, which is not shown here, they appear in sets of 7, right? If you go through the same process, you'll see that for the F subshell, there are 7 F orbitals. Okay, in terms of the actual picture of the distribution of electrons, if you were to plot, and this is a thing for the 1s orbital for an atom, if you were to plot the square of the wave function versus the distance from the nucleus, this is a plot that you will get. However, if you do a different plot where you take into account the volume that is occupied by electrons plotted versus the distance, you're going to get something looking like this. Basically, what this shows you is that the probability of finding the electron would be represented by the maximum right here, and you can drop a vertical to find out what the distance is, right? So this plot is basically showing you how the probability of finding an electron within a volume versus the distance from the nucleus, right? And as a result of this, the picture that we get as far as the s orbital is concerned is that it has a shape, a spherical shape, like a ball, right? So that is what is being shown here. And you remember what I was telling you about taking pictures of electrons and ... and all that. That's what is demonstrated right here. All right, that's the shape of the s orbital. So remember now, an orbital basically shows you it's a region in space where the probability of finding electron is highest, right? So that's what that represents. It doesn't mean that you cannot find the electron outside of that region, but the most likelihood or the greatest probability of finding the electron is within that region, all right? And then that is for the s orbital. Now, that is for the 1s orbital. Now, for the 2s orbital, it's the same shape, but guess what? There's a region here which is called a node, right? Or in this picture right here. That's the result of this plot right here. Actually, this plot, right? Where the probability increases here and then falls down to here to 0, which is corresponding to the node, right? The node is basically that region where the probability of finding an electron is 0 in that region, right? And then what you'll find is that when you get up to the 3s orbitals, there are 2 nodes, 4s orbital, 3 nodes, and so on. So the number of nodes increases for the s orbitals as you go up the higher energy levels. Okay, in terms of the shape of the p orbitals, this is basically what they look like. In some textbooks, they describe it as a dumbbell shape, right? And remember though, p orbitals appear in sets of 3s, right? So that's what these 3 here is what they look like separately. And you'll notice that they are mutual right angles. If you're familiar with the 3-dimensional Cartesian systems in math, right? You have the x, y, and z axes, right? So basically you have the p orbital here, which is aligned along the x-axis. We call that the px orbital. This is aligned along the y-axis, that's a py orbital, and this is aligned along the z-axis, which is a pz orbital. So this is what they look like separately, but in actual fact, collectively, this is what they look like, right? Okay, so that's the p orbitals. And then the d orbitals are even more complex. I don't even expect you to memorize the shapes of these, but this is what they look like. There are 5 of them. 1, 2, 3, 4, 5, and this is what they look like collectively. And I'm not even going to show you the f orbital because that's even more complex, right? But remember, what you need to remember is the number of the different types of orbitals within each subshell. 1 for s, 3 for p, 5 for d, and 7 for f, all right? And okay, so we have just dealt with 3 quantum numbers, but as I said before, there's a 4th one. And that is called the electron spin, right? And the symbol for that is ms. And we're going to see the importance of that in the next chapter when we start talking about electron configurations. So basically, as far as electron spin is concerned, this is the simplest one to understand because there are only 2 values, right? And this is as a result of the effect of, or the property of electrons in an atom. It was found that their spins are quantized, right? And in the case of electrons, there are only 2 possible directions of spins, right? Clockwise and counterclockwise, as you can see here in this diagram. And therefore, the spin numbers are given here. ms is equal to plus half, which corresponds to the electron spinning in that direction, and ms is equal to minus half, which corresponds to the electron spinning in the opposite direction. The thing about spins of any moving charge, and if you have not done physics yet, you're going to learn this in physics. It generates a magnetic field, right? And basically we go by, when it comes to the direction of the spin, we go by the direction of the magnetic field that is produced. So in the case of this diagram right here, where the electron is spinning in this direction, the magnetic field that is generated will be going up like this from north to south. And if the electron is spinning in the opposite direction, then the pole of the spin of the direction of the magnetic field would change in the other direction. All right. And I remember when I was doing physics, there was a right-hand rule that is used to make predictions as to the direction of the magnetic field. Basically, the right-hand rule says that if your fingers, for a negative charge, if your fingers show the direction of the spin, then your thumb shows the direction of the magnetic field generated, right? So that's what is happening in this diagram right here, right? If the spin is in this direction, then the magnetic field is pointing north to south, and the opposite will be true if the spin is in the opposite direction. So those are the only 2 spin possibilities for electrons in an atom, right? So therefore, that's it as far as the spin numbers are concerned. And this was discovered by a guy by the name of, well, 2 guys, Stern and Gerlach. I won't go through the details of this experiment, but basically, this is the diagram which represents the setup for their experiments. And they found that if you have a stream of silver atoms passing through a pole, 2 different poles of a magnet, then basically this the stream of particles was split into 2. And they did some investigation and found that that is due to electron spins, all right? So that's how they came up with those 2 values. Okay, so that's pretty much it for this chapter. So now we should be able to, what time is it? Oh, shoot, okay. We may not be able to finish assignment number 7, but we'll try. All right, so this question, the last question, is testing your understanding of the rules that we just talked about in terms of the quantum numbers. So just to remind you, the possible values of n would be, do it over here, n can be equal to 1, 2, 3, and so on, right? L is dependent on n, where L is equal to n minus 1 and all integers to 0, all right? And then ML is dependent on L, in that ML can be equal to plus L, all integers through 0 to minus L. And then finally, MS can only have one of 2 values for an electron, plus and minus half, plus or minus half, all right? So those are the rules that you're going to apply to answer the question, which says Which of the following are possible for an electron in an atom? For the sets of quantum numbers that are not possible, state what is wrong with each set, and that's it. Okay, so the first one, they gave you n is equal to 1, L is equal to 0, ML is equal to 1, and MS is equal to plus half. Is that possible? Based on the rules that I just wrote above. N is equal to 1, L is equal to 0, ML is equal to 1, and MS is equal to plus half. Is that possible or impossible? Sure about that? Let me give you a little hint. If L is equal to 0, what are the possible values of ML?
Just 0.
Exactly. So therefore, it's not possible, right? So therefore, I would write down in the answer here, impossible, because if L is equal to 0, ML cannot be anything but 0. All right? So therefore, ML cannot be 1. All right? Okay. Any questions about that one? Any questions? Okay, let's look at B. N is equal to 9, L is equal to 7, ML is equal to -6, and MS is equal to -half. Is that possible or impossible? It's possible, right? All of those numbers are legitimate in terms of the rules that we just discussed. So the answer for this one is simply possible. You don't need to explain. Just say possible, all right? Okay, let me erase this here. And erase this here. And scroll down. Okay, so this one. N equals 2, L equals 1, ML is equal to 0, and MS is equal to 0. This one is too easy. Not possible because? Right, exactly. So this would be impossible. Oops. Okay, so impossible because MS can only be plus or minus half, all right? Okay, and that's it for that one. D, N is equal to 1, L is equal to 1, ML is equal to 1, and MS is equal to plus half. Is that possible or impossible? Not possible. Why? Exactly. So this would be impossible because if N is equal to 1, then L can only be 0. All right? Okay. Is there another one? Scroll down and see. Okay. Let me erase this here. Okay, so in the case of E, they gave you N is equal to 3, L is equal to 2, ML is equal to -3, and MS is equal to -half. Is that possible or impossible? Sure about that?
It's impossible.
It's impossible because? Exactly. It's impossible because if L is equal to 2, then ML can only be equal to +2 through 0 to -2. and not equal to, it cannot be equal to -3 in any way, right? Oh, so we're actually finished within the time. Okay, so that's pretty much it. So what I'm gonna do now is set up a Dropbox for this one. Okay, let me clear this. Let me go here. Let me go. So this is assignment number 7. And let me go here. Okay, so today is the 4th. Okay, so I'm going to let this be due the 7th. So okay, so all right, so it's now available, the Dropbox that is now available for you to deposit your assignment. All right, so that's pretty much it. For today. So your test is Monday, right? I did not get to send you guys your assignment number, which is it? The gas laws one. Is that 5? I think. I had some technical issues earlier, so I was hoping to have it sent off to you today, but didn't get to do it in time, so I'm going to do it later on this evening. I think I've posted your scores for that one, right? Okay, right. So it's just a matter of the assignments being sent to you. And I also posted the assignment key, so you can look at that to help you to review, all right?
Do you think you could publish the?
Oh, yeah, I'll publish. Chapter 8, right? Chapter 8. This is where we're going to talk about electronic configurations. All right, so that's there. Yes, sir.